Good afternoon, everyone. Um, I'd like to thank the conference committee for this organization. My name is Hisham Bamufleh, and my presentation is about investigation of physical properties and carbon dioxide solubility in ionic liquid solutions using multi-nonlinear regression analysis. The outline of my presentation is going to be an introduction and Cosmo RS, Henry's law constant, sigma profile and surface density, viscosity, solubility, and conclusion. Carbon dioxide capture and storage is currently a practiced technique. However, capturing CO2 has an energy demand, rendering the process to be inefficient. Also, it's costly to completely capture CO2 produced at an industrial scale in large amounts. In post combustion circumstances, the amine-based solvents currently utilized for CO2 capture have several disadvantages, such as volatility, corrosivity, and high regeneration costs. That's why ionic liquids were suggested as a solution for this problem to some of these issues more than a decade ago. Carbon dioxide is responsible for creating the greenhouse effect. Mostly carbon dioxide is produced during the industrial operations, especially in the fossil fuel industries, which is the refineries and petrochemicals, and related into the atmosphere. In the previous centuries, the concentration of the CO2 in the atmosphere were a few ppm, but in the current day and age, it has maybe crossed 400 ppm, which is an alarming situation for the climate. So as a result, it's very crucial to reduce its release into the atmosphere. That's why the solution is very important. The ionic liquids, which is the solvents, has uh, particular characteristics like low viscosity and low melting points around 100 degrees centigrade and negligible vapor pressure. The ionic liquids are chemicals that are safe for the environment and do not cause any pollution. So the fact that the ionic liquids have excellent stability, high CO2 solubility, and also low vapor pressure, these properties make them an ideal for the capturing of the CO2. Cosmo RS, the model for predicting the activity coefficient depict the the non-ideal behavior of the chemicals in solution. This methodology predicts or method predicts the liquid thermodynamics properties by considering the molecular structure and eliminating the need for the experimental data. The method for considering the molecules in the form of the surface segment and calculates the chemical potentials for each segment. These calculations provide an important insight into the molecular interactions. To forecast the activity coefficient of the gases and liquid in ionic liquids, Cosmo RS based model was created. This Cosmo RS is a software, an economical, quick, and adequate method to evaluate the thermodynamics, physical, and chemical and molecular characteristics of the ionic liquids. Henry's law constant value, it's a very important parameter in the gas solubility of the ionic liquids. If the value of the Henry's constant is low, it signifies a higher extent of solubility. It's found that the solubility generally decreased with an increase of the temperature. Henry's law constant also was measured and correlated with the reciprocal of the mass of the ionic liquids. It was found as to be a function of the molar mass of the ionic liquids in case of the dominance of physical interactions between the gas molecules and the solvent. So in this regard, the Cosmo RS can provide a better qualitative analysis and predictions. The solubility of the CO2 in the ionic liquids for the ammonium-based ionic liquids is new and provide a further basis to improve the gas capture capacity of these compounds. So in this work, CO2 solubility performance is determined experimentally for two ionic liquids, which is tetramethylammonium bromide, TMAP, and tetraethyl ammonium bromide, TEAB, is determined. And this is the operating conditions. The pressure is range from zero point 0.5 to 2 megapascal. The temperature range 303 and 313 and 323 Kelvin. Concentrations was ranged from 2.5 to 5 and 10 weight percent. The methodologies that we have the ionic liquid with the CO2, and then we have the run in the COSMO-RS, and then we will calculate the activity coefficient and develop the model at this certain operating conditions. And this is the methodology that we went through in generating the data and using the COSMO software. And this is the experimental setup in which we inject the ionic liquid and inject the CO2 and calculate the amount of solubility of CO2 into the ionic liquid until it reaches to the equilibrium and the maximum capacity of the absorption of CO2 into the ionic liquids. Sigma profile. Sorry. Sigma profile was generated via the lowest energy conformer. The Sigma profile is generated using this software, and it depicts the change, density, and distribution of the whole molecular surface. So it has the analysis of the molecular surface. Then the Sigma profile was used as the basis for this program to predict the desired thermodynamics properties such as the Henry's law constant and activity coefficient. This is the sigma profile that give the range of the hydrogen bond donor and the non-polar region and the hydrogen acceptor of these two solvents. So the region between minus 0.01 to 0.01 is generally considered for the non-polar, and the electronegative region is from 0 to 0.1, while the electronegative region is from 0.01 onward. The peaks in both electronegative, positive and negative region can be observed. It can be noticed that from the profile that the bromide anion is located in the electronegative region, and it shows hydrogen bonding ability. The anion plays an important role in terms of solubility. The cation MAB and TEAB hold peaks in the electropositive region, but the TEAB shows more gas solubility due to the being higher chain length, as more CO2 molecules will get attracted. For the sigma surface, on the cation TMAB and TEAB indicates the electropositive and behavior and the hydrogen bond donor. The green and the blue colors in the structure shows the electropositive behavior in the cationic structure. Bromide is known as a halide anion, and the literature says indicates that halide have good hydrogen bonding ability. That's why this anion is included in this molecule. Also, it can be noticed that the red color in the bromide anion show it's highly electronegative and has a hydrogen bond acceptor capability. And this is the sigma surface shown by the software, and the color indicates, as you see, from the red to the blue, the electronegative, and the electropositive for the blue. And the Henry law, the Henry's law constant, and the hydrogen bonding is calculated. The solubility increase as the chain length of the cation increases, and the higher solubility are correlated with the small value of the Henry's laws, as shown here in this table. As far as density is concerned, for the ionic liquid, the effect of the temperature is known such that the increase in temperature density decreases slightly, which is due to the relative free movement of the molecules. Due to the molecules' kinetic energy-driven separation from one another, as the temperature rises, there are moderate intermolecular interactions between the molecules. Due to the presence of the ethyl group in TEAP molecule, the density is higher than TMAB, which contains the methyl group. It can be noticed that the density of the TMAB at all selected temperatures is higher than the density of TEAB. It's due to the reason that there are more free volume available in case of longer chain length. That's why the ionic liquid with the smaller chain length, that's the tetramethyl group, has a high density due to the less molecular volume as compared to the tetraethylammonium. And this is the results of the density at different concentrations of TEMAB and TMAB for different concentration at 2.5 and 2 and 5% and 10% as a function of temperature, which indicates that it decreases with an increasing temperature. The viscosity also is one of the parameters that is important. Viscosity is defined as the resistance to flow, and the viscosity of the TEAB is greater than that of the MAB due to the increasing length of the cation. So this is because a longer alkyl chain have a stronger van der Waals interactions. These forces are responsible for the attraction between the cation and anions. This makes it possible for them to fit together tightly, so viscosity will be increased as a result. Viscosity increase also with concentration. The availability of the additional molecules grew along the concentration of the ionic liquids. The increase in the concentration results in forming more bonds and increasing the viscosity. All the aqueous ionic liquids at any constant concentration become less viscous as 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 temperature increased, and lower viscosity is a result of the van der Waals forces decreasing at higher temperature. And here is the viscosity also showing at different temperatures for different molecules and different concentrations. When we go to the CO2 solubility at 5% concentration, at this concentration, the highest amount of solubility is found to be at operating conditions of 2 megapascal and 303. In terms of the mole fraction, it was observed as a 0.29 mole fraction of CO2 in the ionic liquids. The effect of the increasing the concentration on CO2 capturing capabilities of ionic liquid is evident. So it's found that the solubility of CO2 at 10 weight percent concentration is higher by a factor of 2.5 is higher than 2.5 and 5%. It is due to the reason that more amount of ionic liquid can dissolve and capture a higher amount of the gas as more sites are available and attached to get attached. The solubility pressure essentials increase linearly with an increasing gas concentration in the liquid, and the pressure zone examined in the current study indicate the typically purely physical solubility behavior. So the CO2 solubility is also affected by the intermolecular forces, for example, van der Waals forces, hydrogen bonding energy, and misfit energy. It was examined that These forces are responsible for the interaction between the CO2 and the ionic liquids. Also, concluded that short-range molecular interactions like Columbus and van der Waals interactions cause solubility and attractions between the molecules and the ionic liquids. Cations with longer alkyl chains were more stable than ionic liquids with a shorter alkyl chain in terms of CO2 solubility. The polarity of the ion and cation plays an important role, and more electropositive behavior of the cation and additional electronegative behavior of anion will impart also van der Waals forces, which will enhance the solubility and the capacity to the system. As a result, this interaction between the CO2 and ionic liquid will be stronger. CO2 solubility, the free volume available between the interionic spaces of an anion and a cation is responsible for better gas solubility. For the high solubility and weaker anion cation interactions are preferred. So free volume is the difference between the van der Waals volume of the ionic liquid and its molar volume. The molar volume of ionic liquid also affect the gas solubility. So the molecules with higher molar volume show higher solubility. So it's due to the reason that higher molecule volume directly depends on the free volume. The value of the fractional free volume is high if the compounds has a larger molar volume, which renders the compounds to be soluble for high gas solubility. So this is also the measurement of the solubility with the different pressures for these two different molecules. And finally, the multi nonlinear regression based on the coefficients. We have several coefficients from A1 to A6. We have this model. So by getting the regression analysis, we were able to find the coefficient and the value of this constant. And the conclusion, the factors which influence the CO2 solubility are pressure, temperature, and concentration. It's very evident and affecting a lot in the solubility of the CO2. The free volume between the anions and the cation contribute towards the higher gas solubility of CO2, as interionic space between the anion and the cation allowed more CO2 to dissolve. TEAP shows better CO2 solubility results as compared to TMAP due to its higher molar volume. And thank you for listening.